welcome to the second presentation of the second week. I am Nicola, and this is the first time I am preparing a video for you. Last week I was unfortunately sick and couldn't create anything, but Marissa and Leo did a great job. And this week from this week on, you will usually hear one or two presentations from me every week. Today, I will talk to you about direct proofs. You already got introduced to the idea of proving things, and there are a few different paradigms which can be used in order to prove a theorem. And in this presentation, we will go over the direct paradigm. So, what will we be covering in this presentation? First of all, we will look at the conceptual idea of a direct proof. I will go quickly through the logical idea of proving something, arriving from a premise to a consequent. Then we will take a look at a few case examples. There are a couple of different ways to prove something directly, and for a few of them we will have case examples. Other ones we will just mention and not specify any deeper. One of these specific ways of proving something directly is a proof by exhaustion, and in the end we will have a look at what proof by exhaustion means. It's also a part of a direct proof. And then maybe quite in the end, I will talk a little bit about what's different to an indirect proof and show you one or two sample exercises. Okay, so in order to understand what a proof is, we first have to take a look at what the thing is that we're trying to prove. In mathematics, the entity we're trying to prove is always a theorem. So let's have a look at a theorem. Here on the slide you can see an example. For a theorem, pi is an irrational number. This would classically be called a theorem in mathematics, and this can be proven. Now if you think back to logic, in logic you already were introduced to theorems, and as you remember, a theorem always consisted of premises, a set of premises, and a consequent. And the logical idea of proving something was to assume the premises as they are given, and then show that from the premises the conclusion follows. And if that was the case, then an argument was called sound. Now in mathematics, things behave quite similar. However, the premise can be much further than in logic. In logic, we always operated with a sort of closed world assumption. So we gave a set of premises, and these were all we had. So no outer world knowledge was needed. However, in mathematics, this would be impractical. So when we state the theorem, pi is an irrational number, then there in fact is a set of premises. The set is everything we know about numbers, about algebra, everything we already know true about mathematics. The definition of pi, the definition of an irrational number, all of these things make up the premise of our theorem. Now, of course, sometimes you get a direct premise in a theorem. But like in this example, this is not the case, and it's always important to bear in mind that when we want to prove something, the truth of all the axioms in mathematics that we already know is given. So that means if we want to prove something, if we want to prove the consequent to be true, it is sufficient to take some axioms of mathematics as we know them, and to show that from them the conclusion follows. This is actually not a bad thing, but this is a good thing. It means that we can take anything we know which is true and show that the consequent that we want to prove follows from it. So it gives us a lot of liberty. We have a lot of ways to prove something. Now, this example right here is not something we're going to prove. Pi is an irrational number is a true theorem. It is a proven theorem. But proving this turns out to be quite a challenge, and we are not up for this challenge. We will instead take a look at a few simpler examples. The crucial point for an argument to be called a proof for us is for all the steps which we take to get from the premise to the consequent to be trivial. So, for example, we have an equation and we want to prove that another equation is true. So we can just transform the equation in ways which are valid, as we know, and if all the transformations of the equations are obvious or understandable to us, then we would call them trivial. Now, of course, bear in mind that trivial is a highly subjective word. Probably you've already heard people making fun of math professors for making hyper-complicated leaps of thought and then just calling them trivial. This is definitely not what we're trying to do here. We're trying to define the word in a useful manner. And therefore we will define trivial for the scope of the course as the smallest transformation step we can imagine, which still makes progress, but is easily understandable. So we will use trivial as a synonym to cannot be simplified any further. If a step or a transformation is trivial, this means it's the simplest step we can take. And to anyone who is familiar with basic properties of addition and multiplication, they will be able to comprehend this step. So after all, this is what proving things is all about. It's about making the logical conclusion from premise to consequent in a manner that everyone can comprehend it. After all, the truth or falsehood of a mathematical theorem is completely independent of whether a human is able to understand it or not, or is able to prove it or not. Proofs are not there for mathematics, but they're here for the humans who are doing the math, and therefore it's important to be comprehensible. To be comprehensible is a core aspect of a mathematical proof. And therefore we will take a look now at a few examples, and I hope they will be easily comprehensible to you. Our first example states, if an integer n is odd, then its square is odd. Now we take a look at this statement, and we try to make up our mind how we are going to try to prove it. Now first of all, we ask the question from logic, what is the premise and what is the consequent of the statement? As we already know, the premise contains all truths about algebra that we already know, but additionally it also holds a premise that there is an integer n and it has the property of being odd. This is important. And then the consequent, the statement we're trying to prove, is that n squared is odd. So let me give you an example of a pretty straightforward direct proof. We have our laws of mathematics and the fact that n is an odd number. Now we try to follow that n squared is an odd number. So, first of all, what does it mean for a number to be odd? It means that it is not divisible by 2. And since every second number is divisible by 2, we can express an odd number, as it's written on the slide, as 2k plus 1. K is also an integer, which is divisible by 2, so k is an even integer. 2k is an even integer. K is just an integer, and then 2k is an even integer. And then 2k plus 1 equals n. this is how an odd number is defined. And now, since we have expressed n as 2k plus 1, we can just plug this in to n squared and see how it behaves. So 2k plus 1 is our go-to odd number. If we square it, we get 2k plus 1 squared. This is, as many of you probably know, the first binomial formula. I've written down on the slide the basic transformations. So we have 2k plus 1 times 2k plus 1. And if we outmultiply everything, we get 2k times 2k, which is 4k squared. We get 2k times 1 and 1 times 2k, which is 2k and 2k, or 4k. And 1 times 1, which is 1. And now, if we group the first three terms together, we get 4k squared plus 4k. And there, we can outmultiply a 2. So the step from the third to the fourth equation, we just take a factor of 2 out of 4k squared and out of 4k, which leaves us with 2 times some number plus 1. And as we know, the definition of an odd number is that it can be expressed as 2 times some integer plus 1. This means that n squared is per definition an odd number, and we have proven our theorem. Now, a legitimate question is, if I'm faced with a theorem like this, now this was of course a very simple example, but even in such a simple example, how do I come up with the steps that lead me from the premise to the consequent? And unfortunately, this is a difficult question which does not have a simple answer. To make a direct proof just means to find a set of trivial steps which take us from P to Q in our statement, from P, Q follows. But we don't know how simple this path is. Sometimes for very simple theorems, the path is kind of obvious. We look at the theorem and we're like, alright, this follows from that, and our consequent follows from this. However, it is possible that the proof is very, very far away, and we have no idea which path to take to get to the result. And the answer to the question, how do we get to our result, how do we find the right path to get to the consequent, is that you basically need experience for this. You have to have seen some example proofs for similar theorems. You have to have encountered methods which you can try using yourself, and you have to not be afraid to fail. Just because there's a promising idea to prove something, it doesn't mean it will work out. And if you're faced with having to prove something, and it looks like this proving idea should work but it doesn't, it may not be the issue that you have made a mistake. The issue may just be that this just doesn't work and you have to try something else. An important upside with this issue is that even though finding a proof in itself can be quite difficult, there's usually not just one way to prove something. Oftentimes you'll find very, very short, elegant proofs, but in mathematical theory there is no difference between an elegant and a complicated proof. By now there's been over 200 proofs to Pythagoras' theorem, and they're all mathematically equivalent. Maybe if you go on the Wikipedia page you will find a very simple half-page proof, but over the time this has kind of become a pet peeve for mathematicians. There have been highly complicated modern proofs of Pythagoras' theorem, and they're all equivalent, right? They're all a set of trivial transformations, just sometimes a lot of them, and they all prove the same thing. So the key when trying to prove something is usually to not try reinventing the wheel. You should stick to the methods you already know. You should try to get inspiration from proofs for similar problems, and usually when you've gathered a bit experience in, well, either having read proofs or having proved things yourself, you gain the necessary experience, and when you see a problem, you just start to get a hang of it. You just start to have a feeling, okay, this is this type of problem, probably this method works. But don't get hung up on it. There's even provably theorems which are impossible to prove without mathematics, within mathematics. There's provably theorems which are impossible to prove within mathematics. So don't get hung up if you have troubles proving something. Some problems are tremendously difficult, and this is just in general a very complicated field of mathematics. Now to a special case of a direct proof. Sometimes our theorem does not have the typical structure of here's our premise and here's our consequent. From all of mathematics and a couple of more premises, statement Q follows. But sometimes the type of statement is from P follows Q, but from Q also follows P. Or, as we would say in logic, P if and only if Q. This kind of statement is called a bijection, and it can be usually just treated as two conditional statements from P follows Q and from Q follows P. So usually you can just treat them as two separate statements which both have to be true simultaneously. If such a bijection is true, the statements P and Q are considered to be equivalent. However, when proving such a theorem, one has to be careful. You either have to prove that from P follows Q, and then prove that from Q follows P, or you have to show that P is directly equivalent to Q. Here is an example. We have a theorem. An integer is even if and only if its adjacent integers are odd. Now, in order to prove this, there's two ways to do it. Either we can show that an integer is even and its adjacent integers are odd, are equivalent, but then when we start with one statement, we can only use equivalencies to get to the second statement, or we can show both conditional statements. That is, we can show if an integer is even, then its adjacent integers are odd, and then we can prove if two integers are odd, or we can show if two integers with distance 2 are both odd, then their in-between integer is even. So let's take a look at the proof. First we show the first direction. So if an integer is even, its adjacent integers are odd. So let n be the integers. Let n be the integer. Since it is an even integer, it can be expressed as 2k. K is just another integer, and by this we just express that n is divisible by 2, which is the definition of being even. This means that its adjacent integers are 2k plus 1 and 2k minus 1. And those are by definition odd numbers. Okay, so now we have proven the first conditional statement. Now the second one is we have odd integers n and n plus 2. And now, since they're odd, we can rearrange them. So let's say that n is 2k plus 1, an odd number, and then n plus 2 obviously is 2k plus 3. So now we can find their in-between integer. This would be 2k plus 2, which can be expressed as 2 times k plus 1. And then again we have a number of the form 2 times some integer, which is by definition an even number. So you see we split the theorem into two parts, and usually that's the simplest thing you can do. If you ever encounter such an exercise where you have to prove an if and only if statement, just break it up into two if statements and prove them both separately. That's like the safest way to not make a mistake. And now the last type of direct proof we will talk about with an example is proof by exhaustion. Maybe if you have studied cognitive science so far, you may have encountered this in German as Fallunterscheidung. This means that you take a complicated problem which you have to prove directly, and you basically break it down into subtasks which then are proven individually. Now, of course, when you break a problem down into subtasks, technically an individual subtask may be proven by an indirect type of proof. But the whole type of breaking a problem into subproblems is called proof by exhaustion, and it's a paradigm of direct proving. Here it is important what kind of statement we have and how we are separating it. For example, if we have a statement such as all integers have this and that property, then proof by exhaustion doesn't work. Because proof by exhaustion would mean, well, we look at the first integer, then we look at the second one, then at the third, then at the fourth, and so on. And the problem is that we have an infinite number of integers. So if we have a statement like all integers do something, then we cannot prove this by exhaustion, because there is no way to exhaust all integers by looking at them individually. So you have to remember, proof by exhaustion only works by breaking down your problem into a finite number of subcases. If we have an infinite number of subcases, then the direct method of proving it would be proof by complete induction. We'll get to this later. There is another chapter, an entire other chapter on this. So the goal of reducing your problem to subtasks is to just reduce the complexity and have smaller subtasks which individually are simple to prove. A famous example, maybe you've heard of it, is the four-color theorem. The four-color theorem describes the statement that every single two-dimensional map containing countries, or, well, mathematically speaking, regions, can be colored with four different colors in a way that two regions sharing a border never have the same color. Maybe you've seen a world map printed out somewhere where every individual color is, where every individual country is painted in a different color, and this theorem states that every possible map like this can be painted in four different colors without having two regions sharing borders having the same color. This problem was a very long time unproven until 1977, and it was proven by exhaustion. The mathematicians found that there is a set of, at the time it was 1,834 different maps to which every possible map could always be reduced to. So they found a way to say, no matter how large your map is, there is a deterministic way to reduce it to one of these 1,834 different maps. And what they then did is they proved that there is a four-color assignment for every single one of these 1,834 maps. This was done using computers, but it was an incredibly long proof by exhaustion. It's not elegant at all, but this solved the problem at the time. A simple example for exhaustion is the following statement. Every prime number greater than 3 is A good example for proof by exhaustion is the following. Every prime number greater or equal to 3 is either 1 greater or smaller than a multiple of 4. So, what does this mean? This means that if you have a prime number, it can be either expressed as 4k plus 1 or 4k minus 1. Now, first thing we want to notice, if a number can be expressed as 4k minus 1, this means it can be expressed as 4k plus 3. These two things are equivalent. For example, if you have the number 7, it can be expressed as 4k plus 3. It's 4 times 1 plus 3. Or you can express it as 4k minus 1, which would be 4 times 2 minus 1. Okay, so we are saying that we can express every prime number as 1 greater or smaller than a multiple of 4. So let's have a look at all the numbers. All the numbers are covered by 4 different cases for a relationship with multiples of 4. Either we have a multiple of 4, a multiple of 4 plus 1, a multiple of 4 plus 2, or a multiple of 4 plus 3. Now, let's take a look at the first case, a multiple of 4. If we have a multiple of 4, then this is clearly divisible by 4, so no multiple of 4 can be a prime number. If we take a look at the third case, a multiple of 4 plus 2, well, 4 is divisible by 2, and then we're adding 2. So every number of the form 4k plus 2 is also divisible by 2. So by definition, not a prime number. So this leaves us with 2 cases, 4k plus 1 and 4k plus 3. Now, these numbers can be prime, but perhaps they're not. This doesn't matter. The point is that we have eliminated case 1 and 3. This means that the only types of numbers which are left for prime numbers are 4k plus 1 and 4k plus 3. At this point, it's maybe possible that there are no primes of the form 4k plus 3, but this doesn't matter because we have definitely restricted all the primes to this, and this proves our theorem, just by exhausting all possible cases of having a relationship with 4k, with being a multiple of 4. Now, some of you might wonder, what's the difference between a direct and an indirect proof? Well, the difference is simple. The point with a direct proof is that you have a statement which defines your theorem, consisting of premises and a consequence, and that's what you're working with. So in a direct proof, that's all you're working with. You're not touching upon the logic of your statements. Whereas with an indirect proof, what you basically do is you mess with the logic. So you either negate your statement or do something else to change the statement of the theorem in order to get an equivalent statement which happens to be easier to prove. We will have a look into such methods in the 4th chapter. And in the next chapter, in the 3rd one, we will talk about a very big paradigm of direct proofs, which are proofs by induction. Now, we're done with the content of this video. Now we have some sample exercises for you. The first one, you are given the following theorem. Consider 2 integers m and n. Their sum is always even. What is the premise and what is the consequent of the theorem? And can you find a simple proof for the theorem? Now, it's best if you can just grab a piece of paper and a pen and try solving this by yourself. You may pause the video and take as much time as you need, and afterwards we'll go over a solution. Now, for those of you who solved it, you are excellent solvers of simple algebraic direct proofs, and for those of you who just want to enjoy the show, here's the solution. The premise of the statement is that the two integers m and n are odd, and all axioms of integer addition, so everything we know about adding integers together. And the consequent is m plus n is even. So we will use here a technique which was already used twice before in the examples. We just rewrite m and n as composite integers 2k plus 1 for m and 2j plus 1 for n. So they are defined as an odd number. And now we just take these expressions and sum them both together. So we get for m plus n 2k plus 1 plus 2j plus 1, which is just 2k plus 2j plus 2. And here we can multiply out a factor of 2. So we get m plus n equals 2 times k plus j plus 1. And as always, we get an expression k plus j plus 1, which is just some integer, and then times 2. So m plus n is by definition an even number. And now for the second sample exercise, we're given the following theorem. Consider the equation a to the power of n plus b to the power of n equals c to the power of n. And let n be an integer greater or equal to 3. There is no set of integers a, b, and c such that the equation is satisfied. Now again, take a piece of paper, take a pen, and try to find a solution to this theorem. Now don't worry if you cannot find a solution to this problem. It can be quite a challenge. That's all I have for you today, guys. Hope to see you next week, and take care.